Physics Notes, Unit 23, Part C. And here we have three very similar devices that make use of magnetic induction or electromagnetic induction, Faraday's Law. Bottom line is these three devices are very similar, and you can almost easily convert one into another. Let me explain. So all three of these devices, that I'll explain here in a minute, have at least a coil of wire, or a coil of wire, sometimes two or three coils of wire, and a magnet or magnets. All right, let me spell that right. A magnet. And like I say, sometimes several magnets. So several coils and several magnets makes it fancier. But here are simple depictions of three devices, of which we've talked about before, at least some of these. A galvanometer. And what we've used a galvanometer for in our unit on electricity is as a current detector, an ammeter or a voltmeter. Bottom line is, all three of these things have a coil of wire in a simple case like here. There's a coil of wire around this middle core, and that could be air right there where I'm pointing at right now, but it's usually wrapped around something. And that coil of wire is connected to an axle that's connected to a pointer, a needle, that can detect current. Let me explain. There's also a spring in here that tries to keep that needle in one spot. If you push the needle one way, the spring tries to bring it back the other way, kind of like Hooke's law. But they're specialized springs. They're really tiny. Anyway, there's usually two wires coming out of here. The two wires are the two ends of the coil. Inside there could be a coil with 50 turns. And then the two ends of the wire come out, and you either attach your exterior measuring device or component you're trying to measure to those two pieces of wire that are coming out of your galvanometer. And there's been pictures of the galvanometers in previous notes. And when you put current, basically it's just all those two wires are connected to is the coil inside here. And if you have a device exterior that then, like a battery, that creates current, all right, or you put this galvanometer in a circuit in series to measure current, current goes through this galvanometer, through that coil of wire, and when current goes through that coil of wire, it's magnetic induction. It creates a magnetic field very intense in the middle of that coil, and then you have that generated, that induced magnetic field around the wire, around the current carrying wire, that interacts with the permanent magnetic field that in this case is from north to south, because I have the North Pole. So there's a permanent magnetic field that's going this way, a pretty uniform magnetic field that's always there. And then when the coil of wire has a current in it, there's a second magnetic field that will be in a different direction, and it's circular, so it can't even line up. It's not linear. It's a circular magnetic field that loops around and very intense in the middle of that coil, and they interact. And when they interact, they try to line up, and there's forces that's what causes the needle to move. And then the more current you put in that coil of wire, the more that needle wants to move. And if you take the current off the coil of wire, the spring brings the needle or the coil back to its original spot. So if you put more voltage in there, you get more current, or if you just have something that's so that you can measure, you could use it as a voltmeter, because the more voltage you put in there, double the voltage, you'd have double the deflection on that needle. Or just put more current in there. So you can, depending on how you hook it up, you could use this as an ammeter or a voltmeter, because there's two interacting magnetic fields. Same thing is basically happening in all these other devices. In fact, this galvanometer, if it weren't enclosed in a case, and if there wasn't something limiting the needle from going too far, it could act like an electric motor, like this thing over here. Now this middle one is more conducive, or it's hooked up to be more efficient as an electric motor. But let me explain. Like, for example, this needle here, if the needle were allowed, it could go all the way around. If you let the current go all the way around, it could spin like an electric motor. So it could be easily turned into an electric motor if you change the physical hookup of the container it's in. For example, this looks a lot different, but it's basically the same idea. You have a north pole and a south pole, so you have a magnetic field that goes down this way because of the permanent magnet there. It's a horseshoe magnet, basically. And then if you have a coil of wire, okay, but it's usually several coils of wire, and it's connected to this fancy like armature with brushes. I've shown you some pictures of that previous to this. But bottom line is, if you connect an electric or a battery like even an electric car or anything with an electric motor, a fan, if you put electricity into this, then the current flows in that loop, and it's usually several loops. So it's yellow in this case. It's one single loop. But there's a torque on that loop. We've already calculated torque on a loop because when the current goes through that yellow loop, there's a magnetic field that interacts with the red magnetic field already there. And once again, that creates forces that try to turn and turn that loop. And because of the way it's hooked up with what's called a split ring commutator, which you don't need to remember, it causes this torque to be in one direction at all times. Because the torque, if you don't make some fancy connections here, the torque is going to first try to make it turn one way, then the other way, so it won't turn freely in one direction, which is what you want for an electric motor. Okay, so you have to have a fancy hookup here. It's not that fancy. So you have to have a consideration for that, and you also have to have brushes that rub so they don't twist up the wires, because the wires will get twisted up if you keep turning something. But bottom line is, the torque generated causes the loop to turn because there's two interacting magnetic fields. And the generator is just the opposite of the motor. In fact, you can have these two things almost be interchangeable. There are devices that can work both ways. But we're not going to do that right now. But generators basically are totally making use of Faraday's law of generating electricity. Once again, it's very easy to generate electricity. You just have to move a magnet or spin a magnet or spin a coil of wire by a magnet. Move your conductor, spin your conductor by the magnetic field. Once again, there's a magnetic field here straight down because of the permanent magnet. You can see a lot of similarities here, and you have a loop of wire or several loops of wire. But in this case, what's being put in here is you spin the wire. Okay, you spin the wire. This is the Faraday's law effect. Okay, and as you spin the wire, the coil, it generates current in the wire, but it takes some effort because there's like back EMF, there's a back resistance to your input. You have to put energy in, mechanical energy in, but what comes out is current according to Faraday's law. And you can light up light bulbs or sell it to people who want to run their refrigerators or their appliances at home or whatever device that you need to charge, which we'll talk about in a few minutes. Charging devices using transformers. But they all have all three of these devices have the same components. They have a permanent magnet, usually a horseshoe magnet, or some other kind of fancy configuration of several magnets. These are the simple drawings for these devices. But in the summary here, the galvanometer can detect current. Okay, the more current it detects, okay, because of the induced magnetism, magnetic induction in that coil, it deflects the pointer further. The electric motor, okay, well, the motor, electric motor, not gasoline motor. This is for an electric motor. Converts electrical energy to mechanical energy. So you put in electrical energy, it creates a magnetic field in the loop, and then there's a torque on the loop, and the loop starts to turn, and you can connect it to fan blades or the wheels of your car, and you have an electric motor. And then finally the generator, right, which is making use of the Faraday's law directly, converts mechanical energy to electrical energy. So the motor and a generator are exactly opposites. Okay, they have opposite inputs. The generator, you put in mechanical energy, and it's transformed to electrical energy. The motor, you're putting in electrical energy, and it's transforming to mechanical energy. All right, so three similar devices that make use of magnetic induction and or electromagnetic induction. All right, so now in the generator, when you're turning that coil, and you can do it manually, which is not efficient, like they show in the picture, or you could do it by steam that was heated up by coal, not preferable, or natural gas, or a nuclear reaction, or air over windmill blades, or water over a waterfall, hydroelectric. So all those generators are providing the rotation of rotating the coil in a magnetic field. The only type of energy basically that doesn't have that particular setup for generating electricity is solar. Solar is a direct conversion from sunlight into electrical energy. The other ones are from some kind of stored chemical energy or kinetic energy of water falling or kinetic energy of wind or the chemical energy in the burning fossil fuels or the chemical energy, the nuclear energy in nuclear fuels that generate heat and turn it to steam and turn some coils of wire. But like I say, solar is the only one that's directly converting sunlight into electricity with no moving parts. And we're getting better and better at solar. I mean, obviously the issues with solar are that sometimes it's not always sunny. Also, there are some issues with making the solar panels. There's some toxic chemicals it takes to make the panels. That's a discussion for another day, but we're getting better at solar. But bottom line is, in most generators, you're rotating a coil. And here's an equation that gives you the maximum voltage that can be generated or supplied as you turn that coil. Now, automatically, it's alternating current because it's kind of like moving a magnet in and out of a coil. And you can use fancy hookups and other electronics to smooth it out and make direct current, but really it's more advantageous to leave it as alternating current for reasons you'll see here in a few minutes. When it comes to transforming one voltage into another voltage, it's advantageous to have alternating current. That was a big discussion and argument between Tesla and Edison. Maybe you saw that, some videos on that. I'm not going to get into that right now, but Tesla was the one that wanted alternating current. Thomas Edison was the one that wanted direct current, and there was kind of some big skirmishes with a lot of implications back in the day. You can look it up, it's kind of interesting, but Tesla finally won out, even though Edison became the more famous person and is more celebrated, I guess. You know, we can argue that, but he's probably more famous than Tesla, although now we're pretty familiar with Tesla because of the car company and the units named after him. But anyways, back to this. The voltage and the current, therefore, is alternating. So, but it has a maximum. It's a sinusoidal curve, but all we're going to look at is the maximum. We're not going to study mathematically the sinusoidal mathematical properties. That would be for a future physics course. But bottom line is you can get the maximum voltage supplied by just taking NBA times the rotation rate in radians per second. So by automatically, when you're spinning a coil, it's changing the magnetic flux through the coil of an area A. So it's pretty straightforward. Just got to convert everything to the proper units. So we're going to plug into that equation. I'm going to use this symbol Emax, EMF maximum, equals NBA, omega. Now in this particular problem, we have to figure out, well, we can start plugging in, but I'll have to figure out, I'll do some sub-calculations here in a minute, some side calculations. It says there's 220 turns, right? Yeah, 220, yeah, that's good. It tells me that B is 1.25 Teslas, that's good, units. For the area, I'll do a side calculation, pi r squared, and that is 3.14 pi times 0.06 because diameter is 12, radius is 6. Square that, so we get the area of this particular loop. We had this one last time, I think. 0.011 meters squared. And we want meters, not centimeters. So that's my area. I can put that in, 0.011. Now omega, I want radians per second. Well, I have six revolutions in 320 milliseconds. 320 milliseconds is 0.320 seconds. So 6 divided by 0.320 seconds. That gives me 18.8 revolutions per second. So that's 18.8 revolutions per second when I divide those two numbers. That's revolutions per second. I want radians per second. So if you remember this back in Unit 10 in first semester physics, 18.8 revolutions per second times 1 revolution. 1 revolution is 2 pi radians. 1 full circle is 2 pi all the way around. So that gets rid of the revolutions. So multiply by 2 pi, it comes out to be 118 radians per second. So we had to get to radians per second. So I'm going to plug that in over here now. I'm going to plug that in over there. So that's my last thing. It needs 118. That's 118 there. And then I just multiply those two. That gives me the maximum voltage. It'll oscillate between plus and minus this number as it alternates between plus and minus. That comes out to be, in this case, 360 volts. So that's just the maximum. it'll alternate between plus 60 and negative 360. So it's going to average less than 3, well, it's going to average out to be 0 if you take plus 360 and minus 360. But then there's a peak. If you take the absolute value, there's a peak average voltage. We're not going to get into all that. That actually is outlined in the book in some of the sections that we're not going to get into later in chapter 23. This is as much as we'll do with maximum EMF for a rotating coil of wire in a magnetic field. All right, finally now, transformers. Transforming from one voltage to another. We're not talking about, like I said before, we're not talking about like the movie transformers, like, what was it, Bumblebee? I think it was a yellow car transforming into like a robot. That's not what we're talking about here. We're talking about transforming one voltage into another. And these are very important to us. I mean, all our phone chargers are transformers. Because our phones, basically, the batteries in our phones are, I don't know, 3 or 4 volts, DC, direct current. And the outlets in houses are 120 volts, give or take a little bit. So you have to have, they would fry up your battery in your phone if you try to use 120 volts directly to charge it up. And as we've mentioned before, there's different countries. If you go to a different country, you need other adapters to convert to their particular voltages. You need to transform. But there's even more reason why, even in this country, to use transformers, not just to charge devices, but because, well, let me just give the definition first. It's used to increase or decrease voltage through electromagnetic induction, Faraday's Law. Now, it only works with AC current. Okay, it only works with AC current. You have to have a changing current. So as I was just trying to mention, it's important to energy companies because it's advantageous to transport, in other words, to ship electricity at low currents. In these big wires, sometimes you'll see these out in the country, these really tall towers with all these big wires, and then there's some of these substations that sometimes say, danger, high voltage. It's advantageous for them to have high voltage, low current, because you get less heating loss. It's more efficient. All right, and it saves them money, and theoretically it saves us money because they can get the electrical energy to our homes more efficiently. But you can't have 10,000 volts of voltage in your outlets. So when it gets to the cities or to the corner of your street, even before that, they have other ways. They say what they do is they step it down. So they transport it at like 10 or, I don't know, 100,000 volts. They have these other stations in cities that bring it down to like 10,000 volts. And then at the corner of your street, and sometimes this happens in an electrical storm, you'll say, oh, your transformer at the end of your block got hit. Well, what that is a transformer that's stepping it down. That's the terminology they use, stepping it down from, say, 10,000 volts to 120,000 volts before it goes in your house. Because 10,000 volts could more easily kill you than 120 volts, which still could kill you, especially if you're standing by water. So what they do when they generate electricity out in the country, basically, with either, coal or natural gas or nuclear or a windmill, they step it up. That's the terminology used. They step it up to 10, 100, I don't know what it is, 100,000 volts. And as you'll see, if you have a high voltage, low current, you still have a lot of power, which we'll show you in a minute. Anyways, this device is a little bit different than the other 3 devices I showed you a few minutes ago. The other 3 devices all had a permanent magnet and a coil of wire. All transformers have like an iron donut, which is not a magnet. It's a soft iron, so it can be magnetized very easily. And as they show you in this diagram, the magnetic flux or magnetic field lines can be encaptured by that iron, soft iron, can be easily magnetized. But it has 2 coils of wire. 2 coils of wire. That sometimes are wrapped on either side. Here they show wrapped on either sides with a bunch of different loops. And the key is there's like maybe 20 loops over here and 10 loops over there. So it's a 2-to-1 ratio. That's important, which I'll show you in a minute. So you have a soft iron core. It could be rectangular or square like this, but it has to be a hole in the middle, basically, so you can wrap these coils of wire. Okay, so it has a soft iron donut and 2 coils. It has to have 2 coils. And the one on the left here would be like what plugs into the wall. So that'd be like the two leads that plug into the 2 spots in the wall. And then over here on the other side would be like, you can't really tell you, but the wire that goes to your phone has 2 wires, and it has 2 connections inside the phone. It makes 2 connections, and that's what they call the secondary. That's what's called the output of the transformer, but it's input to your phone to charge your phone battery. So this is what plugs into the wall. It's the primary coil. It's the input to the transformer. Then the output of the transformer goes to your thing you're trying to charge. So the terminology is that primary is the input to the coil, to the transformer, output is the secondary. You have what's called step up. Transformers that step up increase voltage. That's what they do before they ship it into the cities. And then your transformer at the corner of your house and the one that you use for your phone charger is a step down transformer. It steps it down. Your phone transformer that you plug into the wall steps it down from 120 to, like, I don't know, 5, 6, or no, I think it's 3 or 4 volts. You have to look that up, what the voltage is on your phone. And it's also DC instead of AC in your phone. There's other electronic components in there like capacitors and diodes that can take AC and turn it into DC. But the main thing to make this all work, you have to have AC to start with. Because what happens here is, in this primary, so you have current going this way, okay, so it wraps around. So if there's current to the right in that top wire, then there's going to be, it goes around and around and around and around. It comes out going to the left in this bottom wire, okay, because it's one continuous loop. It goes around and around and around and around, okay, and it comes out to the left, okay. But what happens here in an AC current is the current for like 1/60th of a second goes that way, then it stops and goes the other way. So both arrows reverse, forward and backwards, forward and backwards, forward and backwards. So it's alternating current. But as the current goes, say, to the right here, if you use the right-hand rule number 2, that will make, as the current goes to the right, it's like putting a magnet in this iron core that goes this way around. So those dashed lines all there, the magnetic flux, when the current goes to the right in that coil, okay, using this top wire, I think this bottom wire, they didn't really show it right. It should be coming out from behind that coil. But bottom line is that top wire, I'm not going to test you on the directions. The main thing is the direction changes on this iron core. So as this top current goes to the right, the magnetic field goes this way. And it's like putting a magnet, down like this into that coil. Well, Faraday's law says if you put a magnet down in that coil, you get current. You're going to get current in that, and the direction would be according to Lenz's law. The current will go one way. Then a 60th of a second later, the currents reverse. So this current and this current reverse, but I'll just look at the top one. That current goes that way. Well, I was going to use red. Okay. So the other current, so this current reverses and goes that way. Well, when the current goes that way, it changes the magnetic field. It's like stopping this and then having magnetic field go this way. I guess I'm using red now instead of blue. So it's like taking the magnet going down, which was blue, and now making it go up. So it's like putting a magnet in and out of the second coil. You're changing the magnetic flux, the magnetic field through the center of that coil, and that creates an alternating current on the output side. So it's a very simple, efficient device for transforming voltage. And the ratios are just simply ratios. Here's the equation. And you can write this equation about 20 different ways. Well, maybe not literally 20 different ways. But you have V sub P over V sub S, the voltage in the primary over the voltage in the secondary, equals the number of turns in the primary over the number of turns in the secondary. When I usually teach this, I usually have V sub 1, I have the primary be number 1. So I have V sub 1 over V sub 2 equals N sub 1 over N sub 2. But P and S are probably better to use. It's consistent with the book. Primary is the input. Secondary is the output. But this equation can be, like I say, written in several different ways. It's also, this would be the same equation. You could have V sub S over, you don't need to write this down, over V sub P. This is the same equation. It's equivalent. It's the same equation. It means the same thing. You could flip both sides. Or you could cross multiply. So that's kind of weird. You'd have, if you cross multiply, it's the same equation. You don't need to write this down. You'd have V sub P times N sub S equals V sub S times N sub P. And you can flip-flop a lot of different ways. Like I said, you can probably draw, this is about 8 or 10 ways to do this. But I'll stick with the circle as my starting point each time. Okay. Now, Ohm's law still is in play. That's Ohm's law. V equals IR. And if you have 100% efficiency, we'll talk about efficiency. And a lot of transformers are close to that. They're in the 90s. Because you want efficiency. If you don't have efficiency, then you lose energy, and it costs them more to get electrical energy to your house, and it costs you more, or they lose money. But what's also true is the power in a primary equals power in a secondary. So those three equations are the three equations we're going to use for applications to transforming voltages, stepping it up, increasing the voltage. If you have more turns in the secondary, this particular transformer is what we call a step down. And the way you tell that is because there's fewer turns, fewer loops in the secondary. So this one would be an example of a step down transformer. There's fewer turns in the secondary. And it's simply a ratio. Look back, the ratio here is about 2 to 1. Twice as many turns in the primary than the secondary. So it'd step it down by a factor of 2. It'd go from like 20 volts to 10 volts or 50 volts to 25 volts if it's a 2 to 1 ratio. Let me give you an example. Here we go. And so we have an alternating EMF. Okay, so we'll just take that as an average or overall or maximum voltage. So we ignore, in a sense, the sinusoidal nature of the EMF provided. But this works. You're simply going to just plug into part A. V primary over V secondary equals N primary, or N is the number of turns, over N secondary. So it tells you 3 of these 4. It tells you that there's 150 turns on the primary, so you have 150, that's the input side. The secondary has 3,000 turns. The, I was putting in, I got to do that over again. I need that, it says the voltage in the primary is 110. Okay, I don't know the voltage in the secondary. The turns, N is the turns. 150, I got ahead of myself there, over 3,000. It still would have worked. Okay, because I can do the turns, 150 over 3,000 equals 110 over V sub S. It still would have worked, but I want to be consistent with my equation here. These are the number of turns, 150 over 3,000. Input, primary turns 150, secondary turns 3,000. Voltage in primary, voltage in secondary. So if you cross multiply there, you get 150 V sub S equals 1,100 times 3,000. If you do all the cross multiplication and solve that, you end up with V sub S, the voltage in the secondary, is 2,200 volts. So that's a step-up transformer. It's a step-up. Step-up transformer. Because the voltage went from 110 to 2,200. You're increasing the voltage. It turns out, just as a side note, if you step up the voltage, you're going to step down the current because you can't get more energy out than you get in. But that's if they're 100% efficiency, you get the same energy. Well, power is related to energy. That's why we're going to say it's the same power out as in. Technically, the same energy out as in. You can't get more energy or power out than you put in. So violation of the law of conservation of energy. Part B, though. What's the primary current? Well, the main way to do this is this. The power in the primary equals the power in the secondary. So P and S are primary and secondary. Well, the power in the primary is the voltage in the primary times the current in the primary. We're assuming 100% efficiency, which is the assumption you will make unless you're told otherwise, equals the voltage in the secondary times current in the secondary, because power is voltage times current. So the voltage in the primary here was given as 110. The current in the primary we don't know, I sub P. The voltage in the secondary we figured out was 2,200. It tells me that the secondary current is 200 milliamps, which is 0.200 amps. That was that number. So if you just do the math here, you multiply 2,200 times 0.200 divided by 110, you get 4.0 amps. That's I primary, I sub P. That's your primary current. All right? And so what you see here, as I mentioned earlier, it's a step-up transformer, because when you talk about transformers, you're talking about the voltage. You're stepping up the voltage. But the current is going down by the same factor. I think the factor here is 20. The voltage goes up by a factor of 20. The current goes down by a factor of 20, keeping the power the same. Part C. What is the power input? So the power input is the power in the primary equals the voltage in the primary times the current in the primary. So the power in the primary is what? 110 volts. And the primary current we just found is to be 4.0. So the power in the primary is 440 watts. Or 440 joules per second. Power input. That's also going to be the power in the secondary. You can do the calculation and you can verify that. But there's the same power if you assume 100% efficiency, which is what you're going to assume, except for, I'm going to give you an example here in number 9, where it's not 100% efficient. It's close, but it's not quite 100% efficient. It's like 90-some%. We'll show you that in a minute. All right, well, let's do it. The power obtained from a transformer is 2,000 watts. That's the power in the secondary. The primary EMF is 110 volts, and the primary current, okay. So what's the efficiency? So here we go. So in part A, the primary power is the primary voltage times the primary current. Oops, I said P. P is primary. So the power in the primary, the voltage in the primary is 110. All right, the current in the primary is 20. So the power in the primary here is really big. It's 2,200 watts. It's a different transformer than the one before. That's the power in the primary. Whoops, that's not my answer. I want the efficiency of this transformer. What does that mean? Well, loosely speaking, E, which is the efficiency, is, this is a loose definition, is the, I'll give you a general definition, is the partial over the total. Let me explain what I mean. Okay, where I'm using the letter E, E means efficiency. Okay, I misspelled it. I-C-I-E-N-C-Y, efficiency. Okay, partial over the total. They want the efficiency here. This is what I mean, partial over total. You can use this for any general definition of efficiency. In other words, you're putting in 2,200 watts. You're obtaining output 2,000 watts. So you're getting a partial. The partial is 2,000. So you're getting 2,000 out of the original 2,200. That's what I mean by the partial. So you end up with, you can't end up with more. You can't end up with more output than input. You could end up with, in the first case, in problem number 8, we assumed they were equal. Same output as input. That's 100% efficiency. If you have 2,200 over 2,200, it's 100% efficiency. But in this case, if you divide that, you get 0.91. And usually, you convert that to percent. That's 91%. So we would, you would multiply by 100 to get. But you can say 0.91 is the efficiency. Or you can say the efficiency is 91%. Just don't say the efficiency is 0.91%. It's 91% after you multiply by 100 to convert into percent. And like I say, if you would have got 2,200 watts out of it, put in 2,200 watts, that's a 1-to-1, that's 100%. That's what happened in number 8. I didn't calculate that, but you can go back and calculate it. It's the same, both sides. The secondary would also be 440 watts. If you take the secondary voltage times the secondary current, you'll get 440 watts. You can double check that, but it will be 440 watts in the secondary. But in part B, what's the heat loss? Part B, heat loss, well, it's 200 watts. How did I get that so fast? Okay, 200 joules per second. Because, well, I put in 2,200, I'm getting 2,000 out. So that was the 2,200 minus 2,000. That's how I got the 200 really fast. I've lost 200 watts. There's heat. When I'm transforming here, I get heat. And that's a pretty, for power companies or energy companies, that would be a pretty big loss. You wouldn't, your transformer would heat up and that would not be good. That's basically lost energy. So that's a pretty big loss. It's not a very good efficiency. So there we go. We have magnetic induction, creating magnetism around a wire due to currents in the wire. All right? That's where magnetism comes from, currents in a wire. Where does electricity come from? Okay, moving the magnets by a wire. It's the reverse effect. In both cases, you have to have motion. So we call that electromagnetic induction, creating electricity from a moving magnet, or the relative motion of a magnet by a conductor, most efficiently by a conducting loop of many turns. And then we can calculate the EMF for a generator, and we can calculate the transformation of voltages, which is very useful for stepping up voltages and stepping down voltages using a transformer. All right, so that is Faraday's Law in a nutshell, electromagnetic induction creating electricity.